This video will help you to complete the analysis questions for the experiment entitled Finding a Constant Kc. The reaction that you studied was the reaction of iron 3 plus ions with the thiocyanate ion to produce the iron thiocyanate ion FeSCN2 plus. The reaction is given on the first page of your lab. For analysis question 1, you're asked to write the Kc expression for the reaction, which is something that you should be able to do. It's the equilibrium law. So you need to do that on your own. Question 2 asks you to calculate the initial concentration of iron 3 plus based on the dilution in each of the test tubes 1 to 4. So if you recall, you had 4 test tubes that you labeled trials 1 to 4, and in each of those solutions you put 5 milliliters of the stock original 0.0020 molar iron nitrate. So what we want to know is the concentration of the solution of the equilibrium. So you started with a beaker with the iron 3 plus in it, and you took 5 milliliters of that and put it into a test tube. Okay. You also added thiocyanate ions and water. Okay. So for the first one, you actually added 2 milliliters of the thiocyanate and you added 3 milliliters of water. In each of the scenarios, the final volume that you had in the test tube was 10 milliliters, and that's important to note. What we want to know is the concentration of the iron ions in this test tube once all of the substances have been added. So what we need to do is a dilution calculation. The dilution formula is C1V1 is equal to C2V2. The original concentration of the iron solution, so the solution that came from this beaker, was 0.0020. So that's our C1. The volume of that solution is 5 milliliters. We're looking for our concentration, and the final volume is 10 milliliters. So recall that when you're using the dilution formula, it's okay to use milliliters for your volume. If you're more comfortable using liters, that's fine as well. If you solve for C2 here, you find that you get a concentration of 0.0010 mole per liter. So this is the concentration of the iron solution in trial 1. What you'll need to do is create a little chart, okay, of the concentrations for trial 1, 2, 3, and 4. Okay, and what you can do is determine the concentrations of iron in each of those solutions and fill in this chart. Okay, what we're going to end up doing is adding also the thiocyanate. So take a few minutes and do those calculations or determine those values. The next question is to calculate the initial concentrations of thiocyanate. So at the moment, you've got a little chart that has the concentrations of iron in each of the test tubes. Now what we're going to do is calculate the concentration of this thiocyanate in each of the test tubes, trial 1 through 4. It's the same scenario where we have a dilution. So for example, in trial 1, you added 2 milliliters of the thiocyanate ion. So if we look at C1V1 is equal to C2V2, the initial concentration of the thiocyanate was the same, 0.0020. In this case, the volume initially is 2. We're looking for the final concentration. And the final volume, again, the total volume of the solutions in the test tube is 10 milliliters. So we can calculate C2 from that. So the concentration of thiocyanate in test tube 1 is 4 times 10 to the negative 4 moles per liter. Now pause the video, take a few minutes, and determine the concentrations for trial 2, 3, and 4. And you'll have a nice complete chart here where your data is all organized. Now, in order for us to be able to calculate the equilibrium concentration, the biggest thing for us to determine is the concentration of this iron thiocyanate ion at equilibrium. Recall that this ion is red in solution, so this is the substance that was absorbing the light when we shone the light in the colorimeter. So we're going to use some information and the fact that there's a linear relationship between absorbance and concentration in order to help us. You had a 5th test tube that you called trial 5 when you measured the absorbance. I gave you that solution, and that was a standard solution. A standard solution is one where we know the concentration. What we were dealing with in that particular test tube is the following scenario. I prepared a solution for you where the concentration of the iron in the test tube was 0.18. And in the solution, the concentration of the thiocyanate was 0.0020, or 2 times 10 to the negative 4. As you can see in this scenario, the iron ions are largely in excess. The amount of iron that we have in this particular system is much, much, much greater than the thiocyanate. So our thiocyanate is our limiting reactant in this case. And what we've done here is we've set up a reaction which is normally in equilibrium. And what we've done is we've forced the equilibrium to be as complete as possible. We forced the reaction forward. So we want to view it as being a complete arrow in this case. The reason I'm able to say that is because there was such an excess of iron that the iron basically forced the thiocyanate to react with it. So in our standard solution or solution of known concentration, what we have is a concentration of thiocyanate of 0.0002 mole per liter. So this is our standard. We know the concentration of the thiocyanate. We also know, because we measured it, we know the absorbance of this solution. I'm going to use an example of an absorbance of 0.850 for the standard solution. You should be using your value to do the calculations, but you can use this model to help you. I said before that there's a linear relationship between concentration and absorbance. Okay. And if the concentration is 0, the absorbance is going to be 0. So it's a line that crosses the x-axis at 0, 0. The equation for this line is y is equal to mx plus b. Okay. If we replace the y and the x with the a and the c, what we essentially have here is that a is equal to the slope times the concentration. My intercept here is 0. So if I know the slope of this line, I'll be able to take any absorbance and determine the concentration of a particular solution. So in this case, what I'm going to do is use my standard. I have a standard where I know the absorbance and I know the concentration. So I know my A and my C, and I'll use those to find the slope of the line. Essentially what I'm doing is finding the slope of this line. Once I know the slope and the equation of this line, I can solve for any values I want. So for any absorbance, I can determine any concentration. So step 1 is to actually find the slope of the line using A is equal to m times c. So 0.850 is equal to the slope times the concentration, which is 2 times 10 to the negative 4. And what I get a slope of is 4,250. Now for AP students, what you need to recall is that this relationship here is actually called Beer's law. And if we were to write Beer's law in completion with the meaning of the slope included, we've got absorbance is equal to A, B, C. So absorbance and concentration are the same. The A times the B is what is equal to the slope. It's got two parts and there's different meanings for each of them. B in this case is the path length, okay, which means it's the length of the path that the light needed to travel through. In our case, it's 1 centimeter. Okay, the cuvette is 1 centimeter squared. And A is the absorptivity constant, which is unique to the substance that we're dealing with. Okay, so that's a little aside, important for AP students only. Now, once we've got the slope here, we've got a relationship, and so we can use for trial 1, 2, 3, and 4, we can use the absorbance that we were given and the equation of our line to determine the concentration of this particular ion at equilibrium. So if I've got A is equal to m times C, for example, if for trial 1, if my absorption was 0.220, I can sub in and find the concentration to be 5.176 times 10 to the negative 4. Okay, so you don't want to lose any significant digits here, so carry at least 4 significant digits while we're going through this problem, because we're going to be using this number a little bit later. Now that's for trial 1. You can do the same for each of the other 3 trials. So make yourself another table, concentration of FeSCN 2+, Okay, you can put EQ to represent this is your value at equilibrium. You've got trial 1, 2, 3, and 4. Okay, so fill in those values. Okay, so take a few minutes and do that calculation. Next, what we need to do is take all of the information that we have and use it to set up an equilibrium ice chart. So an ice chart is really a tool that's going to help us to organize all of our numbers for the equilibrium that we're studying. The I stands for initial, the C stands for change, and the E stands for equilibrium. So what we have to do is take the information from questions 2, 3, and 4 and use that data to help us to fill in this chart. So in question 2, you were determining the concentrations of iron 3 plus in each of the test tubes. Okay, so we're going to set this ice chart up, and this ice chart is going to be for our trial 1. Okay, remember that your numbers are going to be different in some cases. When you look at question 2, you saw that in trial 1, the concentration of the iron ions was 0.00100. The concentration of the thiocyanate was 4 times 10 to the negative 4. Now, before the reaction started, there was none of this red ion in the solution. Okay, so that initially has a concentration of 0. Now, what you determined in previous question 4 is you determined the equilibrium concentration for this ion, the red ion. Okay? And that's really the most critical part of being able to find the equilibrium constant. We allowed this system to reach equilibrium, so that's the concentration of that ion at equilibrium. Okay, and the E in this little chart here stands for equilibrium. So what value we're plugging in here is the concentration of that ion at equilibrium. So what you can see sort of developing here is a study of the reaction. I started with 0 of the FeSCN2 plus, and essentially what I did was I increased the concentration. Okay, and I increased, what I'm going to do is put it as an X. I increased by X, and then this was my equilibrium concentration. Okay. These ones had to go down, okay, while this increased. Okay. What I'm doing here is following the stoichiometry. So if I produced 1 mole of iron thiocyanate ion, I must have used 1 mole of iron ions. So this must decrease by the same amount that this increases. Okay, hence the plus here and the minus there. So for these ions at equilibrium, my concentration of iron ions is really 1 times 10 to the negative 3 minus x, and thiocyanate is 4 times 10 to the negative 4 minus x. The concentration of iron thiocyanate ion at equilibrium is 5.176 times 10 to the negative 5, which is really what our value of x is, because 0 plus x is equaling this 5.176 times 10 to the negative 5. So we know that x is equal to 5.176 times 10 to the negative 5. Okay. Therefore, we've got the concentrations of the iron and the thiocyanate at equilibrium. The concentration of the iron ions is 9.48 times 10 to the negative 4. The concentration of the thiocyanate ion is 3.48 times 10 to the negative 4. Okay. So really, this critical concentration, the FeSCN2+, has allowed us to determine the concentration of the iron ions and the concentration of the thiocyanate ions. Okay, so pause the video, take a few minutes, and you can set up ice charts for each trial. The procedure is exactly the same. And the last step in the calculations is to calculate the Kc for each of the trials. So you've got your equilibrium expression from question 1 in the analysis, and you've got the ice chart that has equilibrium concentrations for each of the substances. So what you need to do at this stage is sub those values into the equilibrium expression and solve. You can set yourself up a little chart if you'd like. Okay, recording the Kc values for each of the trials. Now that you've got the 4 calculated Kc values, in this question you're going to determine the average value for the Kc. At this point, if you have any outliers, any values that are really far away from all of the other ones, you will not include them in your average. The last question is to discuss 2 what-ifs. So unlike last year where you had to write a discussion of results, that's not going to be the focus this year. The focus is on the errors. And what you need to do is think of 2 errors that could have occurred and discuss the what if. So rather than just stating the error, you need to state the error, and then you need to discuss the impact on the Kc. Okay. This requires lots of analysis because you have to think about how your error is going to carry through in the experiment, how it's going to impact the data you collect, the calculations that you do, and in turn, the Kc value. So you really need to tell us, is the Kc going to increase or is it going to decrease? You need to get to that point. And that is what is expected for completing finding a constant.